Now we'll come to this very important model where composition becomes a recurrence. Now, suppose we have a standard form of functional equations where we are given f of fx, it is ax plus bfx. So here what we do is, in such cases, we study the orbit of x under f. We'll define orbit as x naught equals x, then x1 is f x naught, x2 is f x1, basically f of fx naught, and xn plus 1, it is fxn. So this equation, by continuous application of x as fx, will become a recurrence, which we can write xn plus 2 will be equal to axn plus bxn plus 1. So this functional equation will change into a linear recurrence. Now we can solve this recurrence using characteristic equation. We can use a characteristic equation if the equation is linear, homogeneous, and with constant coefficients. So each term, it is power 1. So it is linear and homogeneous, and all the coefficients, they are constant, and therefore we can solve this recurrence using characteristic equation. So for this, what we do is, we'll let xn as r to the power n. So here will be r to the power n plus 2, and this is a r to the power n plus b r to the power n plus 1, which will give us a quadratic equation r square minus br minus a equals to 0, and we'll solve this to find roots of this equation. Now, if this equation has two real and distinct roots, say r1 and r2, then this xn will be given by a r1 to the power n plus b r2 to the power n. If the roots are real and equal, that is, we have r1 equals r2, then the roots are given by xn equals a plus bn r to the power n. And then this third case, when the roots are complex, say r is rho cos theta plus iota sin theta, then its real solution can be given as xn equals rho to the power n cos n theta plus sin n theta. Now let us take up an example. Say, for example, prove that there exists a unique function f defined on 0 to infinite such that f of fx equals 6x minus fx. Now we'll define orbits. We'll say x0 is x, x1 is fx0, x2 is fx1, or xn plus 1 is fxn. Now we can write this recurrence as xn plus 2 it is 6xn minus xn plus 1. Now we let xn as r to the power n. So it will be r to the power n plus 2 equals 6r to the power n minus r to the power n plus 1, which will give us this quadratic equation r square plus r minus 6 equals to 0. So we'll get r as minus 3 and r as 2. So once we have solution to this characteristic equation, we can write xn as a minus 3 to the power n plus b 2 to the power n. Now in the question, it is given that codomain is positive, and if codomain is positive, we cannot have this vector. As n increases, the value of this vector will make the term negative. So your xn will be simply b into 2 to the power n. Now we know x naught is x. So if we put n as 0, we'll get x equals b to the power 0. So this b, it is x. So xn is 2 to the power n into x. And we want x1, which is fx. So x1, which is fx, will be simply 2x. So for this functional equation, we have a unique solution, and this solution is fx equals 2x. So this is the standard pattern. We can use the same technique for similar questions. Say, for example, we are given f3x plus a f square x plus b fx plus cx equals to 0. So here we'll have this recurrence xn plus 3 plus a xn plus 2 plus b xn plus 1 plus cxn equals to 0. And then our characteristic equation will be r cube plus ar square plus br plus c equals to 0. And we can solve it in the same way.